Imagine a tiny brain, smaller than your fingertip, powering your entire digital world. Your smartphone alone holds 62 of these marvels, packed with 90 billion transistors. But how exactly are these incredible microchips made? Get ready to uncover the secrets of one of the most complex manufacturing processes on Earth. Microchips are born in highly specialized semiconductor fabrication plants, or fabs, where an environment cleaner than a surgical operating room is maintained. These fabs are massive, with clean rooms spanning areas equivalent to 8 football fields, housing hundreds of machines, some as large as a city bus, each costing up to $170 million. It's a 3-month marathon of around 940 processes for a silicon wafer to transform into hundreds of CPU chips, each potentially containing 26 billion transistors. Before a single microchip can be made, we need the raw material, silicon. It starts with refining quartzite into ultrapure silicon. This silicon is then melted and grown into a single, perfect monocrystalline ingot. These ingots are then precisely sliced into thin, delicate wafers. A standard 300mm wafer, about the size of a dinner plate, is only 0.75 millimeters thick. Each blank wafer costs around $100. But after fabrication, its value can skyrocket to $100,000. They're incredibly fragile, shattering easily, and each features a barcode and a small notch to orient it correctly within the machines. Inside the fab, the environment is meticulously controlled. Workers wear full cleanroom suits to prevent contamination. Wafers travel in stacks of 25, sealed within plastic containers called front-opening universal pods, or FOUPs. These FOUPs are whisked around the clean room by an overhead transport system, resembling a futuristic highway for silicon. Once at a tool, robotic arms carefully extract individual wafers, moving them through vacuum load locks into different process chambers, ensuring no dust or air contaminates the delicate surfaces. Fabs often have dozens of the same tools arranged in rows to maximize mass production, with some facilities capable of producing 50,000 wafers, or 5 million CPU chips per month. Building a microchip is like constructing a nanoscopic city, layer by intricate layer. At the bottom are the tiny transistors, and above them a complex network of over a dozen metal wire layers called interconnects. Each layer requires a sequence of precise steps using different specialized tools. Throughout the entire process, frequent cleaning and inspection are critical to remove any dust particles and ensure every layer is constructed perfectly. Let's explore the main categories of tools that make this possible. The first crucial category is mask layer tools, central to creating the intricate patterns. It begins with the photoresist spin coater, which applies a light-sensitive liquid polymer called photoresist to the wafer, followed by a soft bake to evaporate solvents. Next, the photolithography tool takes center stage. It shines UV light through a photomask, essentially a nanoscopic stencil projecting the circuit pattern onto the photoresist. Wherever the UV light touches, it weakens the photoresist. A single CPU layer design can be duplicated on a 6x6-inch photomask, and lenses in the tool shrink this pattern by a factor of 4 onto the wafer. The wafer then steps to pattern all 230 chips. A single CPU chip requires 80 different photomasks, each costing $300,000, meaning a CPU visits the lithography tool 80 separate times. After exposure, a developer washes away the weakened photoresist, leaving the desired pattern. A hard bake then hardens the remaining photoresist, forming a protective mask. Finally, a photoresist stripper uses solvents to dissolve and remove this mask layer once its job is done. Next, we have deposition tools, which add materials to the wafer. These tools deposit various substances like metals such as copper or tantalum, insulating oxides and crystalline layers of silicon. Different deposition tools employ unique physics and chemistry principles depending on the material being added. They typically feature a central wafer handling chamber surrounded by dedicated process chambers, each designed to precisely add specific elements or compounds, building up the chip's structure layer by layer. Removal tools are essential for shaping these deposited layers. Etchers use corrosive chemicals or high-energy plasmas to precisely remove materials from the wafer surface. They work in conjunction with the photoresist mask, creating tiny holes or trenches by removing only the exposed material. Another critical removal tool is chemical mechanical planarization, or CMP. This process applies a slurry and uses abrasive pads to grind and polish the top surface of the wafer, making it perfectly flat. CMP is often the final step in a cycle, preparing the wafer for the next layer of intricate circuitry. Material modification tools alter the properties of the silicon itself. Ion implanters use a photomask as a stencil to bombard unmasked regions of the wafer with elements like phosphorus or boron. This process, called doping, creates the p and n regions vital for transistor function. Ion implantation is primarily used in the front end of line during transistor fabrication, adding about 1 dopant atom for every 10,000 silicon atoms, however. This bombardment damages the silicon crystal lattice. To repair this, the wafer is sent to an annealer, which heats it to a high temperature, allowing the silicon atoms to realign and restore the lattice structure. Finally, we have cleaning tools and inspection tools. Wafer washers frequently clean the wafers using ultrapure water, then dry them with nitrogen gas or hot isopropyl alcohol, ensuring no contaminants remain. Inspection tools, also known as metrology tools, are crucial for monitoring progress and detecting defects. A common example is the scanning electron microscope, or SEM, which provides nanometer-level resolution to spot improperly patterned layers or stray particles. Given the 3-month fabrication time, constant monitoring is absolutely essential to maintain quality. Let's walk through an example of how a single metal interconnect layer is built. First, a layer of insulating silicon dioxide is deposited onto the wafer. Next, photoresist is spread, followed by a soft bake. A photolithography tool then transfers the pattern from a photomask onto the photoresist. The wafer is developed to wash away the weakened photoresist, and then hard baked to harden the remaining mask. An etching tool, typically a plasma etcher, removes a vertical column through the exposed silicon dioxide down to the metal vias of the previous layer. The photoresist mask layer is then removed with a stripper. A physical vapor deposition tool fills the exposed pattern with a sequence of metals, coating the entire wafer. Finally, a chemical-mechanical planarization tool grinds down the excess metal, leaving a perfectly flat layer of insulating silicon dioxide with conductive copper interconnects precisely matching the pattern. Remember, cleaning and inspection steps occur frequently between many of these stages. At the heart of every microchip are the transistors. Modern FinFET transistors are incredibly small, with channel dimensions of just 36 by 6 by 52 nanometers, and a transistor-transistor pitch of only 57 nanometers. Above these nanoscopic transistors are the metal interconnects, which act as the chip's wiring system. These interconnects are categorized by their function. Local interconnects move data within a specific circuit. Intermediate interconnects move data within a core, and global interconnects transport data around the entire CPU. Empty spaces between these metal layers are filled with insulating materials, providing structural support and preventing wires from touching, ensuring the integrity of the complex network. Once the fabrication process is complete, the wafer is sent to a separate building for rigorous testing of each individual CPU. Defective or semi-functional circuits are identified and binned. For example, Intel 13th Gen processors might be sold as i9, i7, i5, or i3 based on how many cores are fully functional. The wafers are then transported to another building where chips are precisely cut out using a laser. Each chip is then flipped over and carefully placed onto an interposer, which helps distribute the connection points to a larger printed circuit board, or PCB. A protective heat-conductive cover is placed on the backside. The PCB itself holds a landing grid array for the motherboard and various electrical components. An integrated heat spreader, or eyes, is then mounted on top to help dissipate heat. The entire assembly undergoes final testing before being packaged for sale, ready to be installed into a computer. From a simple silicon wafer to a complex CPU with billions of transistors, the journey of a microchip is a testament to human ingenuity and precision engineering. It's a 3-month odyssey through ultra-clean rooms, involving hundreds of machines and nearly 1,000 individual processes, all to create the tiny brains that power our modern world. If you found this journey from sand to CPU fascinating, give us a like. Subscribe for more tech deep dives, and let us know in the comments what other manufacturing processes you'd like to explore. Thanks for watching.